Hi there, folks. Welcome to another calculus video. The topic of this video is another integration technique known as integration by parts. So this is somewhat of an advanced integration technique. My understanding is that they don't typically teach it in a first semester calculus class, or if you're in high school taking AP calculus, they don't teach this in the AB class, only in the BC. Well, personally, I learned this in AB. Still don't know why, but my teacher taught us this technique in our AP Calc AB class, and that's kind of unusual, is my understanding. Typically, kids don't see this kind of material until they take Calculus BC, or if they take Calculus 2 in college. And this, I feel like it's one of the most difficult integration techniques to get the hang of if you're learning it for the first time. But it is extremely powerful. It helps us to integrate things that without it, we would have no hope of integrating. And you can think of it as kind of the reverse of the product rule for derivatives. We know that for the product rule, if we have two functions, we want to find the derivative of the product of maybe a function u times a function v. We know that the product rule says that this derivative, the derivative of the product, it's going to be the derivative of our first times our second plus our first function times the derivative of our second. So the intuition behind this method is that it is kind of the inverse of the product rule. So let me give you a preview. We use integration by parts on something like this, where we have one function times another function. This is a relatively simple one, but they tend to get more advanced as you progress through the class. Maybe you're learning this for the first time and you see something like this. Well, we don't really have any integration techniques before this to help us grind through some antiderivative like this one before us, like x times the sine of x. Can't use u substitution on this one. None of the trig identities are really going to help us out that much, so we're kind of limited in our options if we really want to solve this thing. So let's somehow connect this to the concept of the product rule for derivatives. So what we actually have is we have this step already. We want to think of this as u times v prime, and then we're going to subtract this quantity from both sides, u prime times v. We end up with the following. We end up with the derivative of u times v, kind of botched that u right there, still a u, minus u prime times v. I don't know why I put the minus there twice. That isn't really necessary. So this is what we're left with. And of course, if we integrate all of this, we get this expression over here on the left, and then we're going to integrate this term by term. So this is going to get its own integral. This is going to get its own integral. So the only reason this looks a little bit different than what we're used to is because in this one, we don't have u and we don't have v, or u prime or v prime. It might seem a bit more familiar if we were to maybe write it like this. And then take a look at this term right here, right after the equal sign, just to the right of the equal sign. We have the integral of the derivative, and it is the fundamental theorem of calculus that tells us that derivatives and integrals are inverses of one another. An integral and a derivative cancel each other out, in the same way that division and multiplication cancel each other out, or addition and subtraction do. So we no longer have a derivative, and this term no longer even has an integral. We're just left with u times v. Or I guess in this case, I replaced u with f of x and v would be g of x. And then this one is just going to be the integral of f prime of x times g of x. My understanding is that this notation is fairly common, but this one above is also fairly common as well. So I might want to just rewrite this one, make it look more like the one we have below with the f of x's and g of x's. This would be the integral of u, and then this would be, we're going to call this dv because originally g of x is what we used for the function v. The derivative of g of x, g prime of x could be written like this. We have uv equals, no, not uv, sorry. I was saying uv, but I meant to say udv. Integral of udv equals u times v minus the integral of v du. And this is really useful because if we look at our equation that we're given, this function, x times sine of x, it's pretty clear that what we have is something that looks like this. Either we want u to be the x and we want dv to be the sine of x, or we want u to be the sine of x and we want dv to be the x. And it does matter. It's very tricky at first to understand which one you want to be u and which one you want to be dv. The way I like to think about it is we want to pick u to be the function that kind of gets simpler the more you take the derivative of. So let's find our functions. We have our x right here. We have our other function right here is sine of x. So I want to find the derivative of x. We have x. We take the derivative of x, we get 1. Take 1, take the derivative of 1, you get 0. So as you can see, we go from a variable to a constant to basically what is the absence of value, to nothing. Zip. Let's do the same thing with our other function. Take the derivative of sine of x. Of course, we get cosine of x. Take the derivative of cosine of x, you get negative sine of x. And then from there, the pattern continues. So as you can see, this one does not get any simpler when you take the derivative. We go from sine to cosine to sine to cosine, and we just flip the sign every few terms. As you can see, this doesn't really have any effect on this function. So ideally, we want u to be the function that gets simpler the more we take the derivative. So that would be x. We want u to be x in this case. U should always be the function that gets simpler the more you take the derivative, and I'll show you why. So u is x, so naturally, whatever is left has to be dv. Not just sine of x, but the dx is also included in that. U is x, so dv is sine of x dx. So if we look down at our formula, we have a u, we have a dv. We need to find v. We also need to find du. Du is pretty simple. Du is just the derivative of u. Derivative with respect to x of 1, or sorry, I got ahead of myself there. The derivative of u with respect to x, the derivative ends up being 1 because our function is x, and when we take the derivative of x, we get just 1. And then a lot of people don't understand this part, but this is how we go from having du dx to just having du on one side and dx on the other. So we start with the derivative. This is the conventional notation for a derivative, but then what we do in an integration problem like this one is we multiply both sides by the derivative. So when I was first taking calculus, I didn't really understand this part. I didn't really understand why du is just dx or maybe something along with dx. In my experience, when we take the derivative of something, we don't have a dx attached to it. And it wasn't until much, much later where I understood why this ends up looking the way it does. We're actually multiplying our derivative by dx, thus moving the dx differential to the other side. So we have our u, we have our dv, and now we need v. V is just going to be the antiderivative of dv. So we want to find the function that when we take the derivative of it, we get sine of x as our answer. Well, you might be thinking it's cosine, but that's not totally right, because if we take the derivative of cosine, we get negative sine. We're not trying to get negative sine, we're trying to get just sine. So what we might want to do is make both of these negative. So this would be negative sine, this would be negative cosine. So this right here is exactly what we want. We're not trying to get negative sine, we're trying to get positive sine. So that means our function that we take the derivative of must be negative cosine, because only then will we get sine of x as the derivative. So this is our v. Function v is the negative cosine of x. So now let's go ahead and plug things into the general formula. So after we have our expression written in terms of a u and in terms of a dv, after that we want to multiply u times v without an integral sign. So this is just an ordinary expression, no integrals in this part. So this is going to be u times v, u is x, v is negative cosine of x. And then we have, next part says we minus the integral of v times du, minus integral of v, which is going to be, once again, negative cosine of x. And then we have times du. Du is just going to be dx. So as you can see, we have a nice and easy expression now. If we came into calculus class after a long weekend and we saw this on the board, if you haven't learned integration by parts, chances are you're not really going to know what to do here. But if you see something like this, this is just cosine of x. This is an extremely simple integral problem. We know that the antiderivative of cosine is just sine. So that's why integration by parts, it's such a powerful tool. We're able to make something we don't know how to integrate into two separate terms. One of them is not even an integral of any kind. It's just a simple expression. And the other one is an integral we know exactly how to solve. So this is just a demonstration of the sheer power that this technique has. It can do things that other techniques can't. We have u and we have not dv, but this is just going to be v actually. And then we have minus integral of v du. So now that we have everything plugged in, we don't need this formula along the bottom of the screen anymore. So let's simplify it a bit. Our integral is equal to negative x times cosine of x. And then we have two negatives, making this net positive. It's a net positive term, cosine of x dx. And then from here, we can leave this part alone. This term right here doesn't require any further manipulation, doesn't require any calculus. We're going to leave this just the way it is, but then we're going to take the antiderivative of cosine of x, which is, of course, sine of x. So there you have it. This is our solution. We're able to take some, frankly, intimidating looking function, something that we may not know exactly what to do with, but we're able to just rewrite it using what's essentially just derivative rules, rewriting it using the product rule for derivatives, and we end up with something we can integrate, and we do. This is our solution.